What are you doing?
I am trying to start a fire to cook my baguette.
Alright, have fun then.
Wait, may I ask you something?
Yeah?
Do you know how long I should cook this delicious meal?
No idea. It depends on a lot of things. Maybe you can simulate it first to see how long is the perfect time.
How can I do that?
Well, that is pretty simple. You need to know the position of every particle in your system, that is your baguette, and their charges, so you can determine how they will interact over time. Also, you would need a supercomputer like that, and a tasking framework like HPX to calculate everything in time.
Wait, what was that image?
Nothing, just an image in your head. Anyway, all of this will allow you to precisely determine the evolution of your system. But yeah, you would need a way to do this fast for a big system. Let's say billions of particles are going to take a lot of time. Maybe you can use FMM, but I'm not 100% sure.
What do you mean by FMM?
If you want, I can explain you what it is and how it works. Just come with me! So you want to know about FMM?
Well, I didn't ask for all of this, but since I'm here, why not?
Alright, so first of all, FMM stands for Fast Multiple Method. It is a method used to calculate interactions between particles in linear complexity instead of n-squared complexity, meaning doubling the size of your baguette will only double the time needed for the computation.
Oh, cool. It might end up before my baguette burns then.
It is really useful because it can simulate complex molecular interactions such as protein folding or interaction between sugar and protein with heat in your baguette. To do that, it makes use of multiple. They are objects that represent a set of particles. They are composed of several complex numbers disposed in a triangle, like you can see in this slide. The triangle shape makes it easier to compute interaction between multiples. Then you would ask, why are we computing multiples for this method?
Well, not really, but since you ask, why?
The idea is pretty simple. Instead of computing every interaction, we are grouping particles next to each other in boxes and then computing interaction between boxes. If the particles between two different boxes are far enough, there is a very small difference from the naive approach, but it's negligible. So if you understood correctly, the first step is to create boxes. This is done by separating the space in our system in half on each axis. We can do this recursively, and the number of times we do this is called the depth. So we have 8 to the power of the number of depths boxes in our system. To reduce the error induced by the simplification of this method, we create a neighborhood from where we apply the naive approach. Here you see a few examples with neighborhoods called WS of different sizes. But in our case, we only use WS equal 1 because it is optimal. And so, for every direct neighbor of our box, we will compute interaction particle by particle. In the end, there are two distinct actions done by FMM. The first one is to create multiples and make them interact for boxes that are far apart. This is called far field. It contains the first 4 passes of our algorithm. And the other one is the one I just talked about, the interaction by particle inside the neighborhood, the near field, which is the 5th pass. The linear complexity of these programs comes from the tree of multiples that we are manipulating throughout the algorithm. In fact, pass 1 is the action of creating multiples from boxes at the extremities of our tree and combining them to go to the root to obtain multiples of groups of boxes. During pass 2, we create local moments for those multiples using a specific pattern so that the resulting multiple contains the interaction from that box to every other box. Right after, in pass 3, we shift down from the tree root node those new local moments until we reach the leaves. Finally, because each box has its own local moment representing its interaction in the far field, we can use this moment to compute a new force to the particles. There, simple, right?
Wow, this is amazing.
If you want, I can run it for you, because Arthur and Tristan, two awesome students from Paris, made it run way faster in parallel using a multi-threaded framework called HPX.
It's way too late. With all your explanations, my bread has turned to ashes.